Now we're going to take a closer look at the periodic table and some of the trends that are associated with its arrangement. But first we're going to talk about history. In 1871, Mendeleev arranged the elements known at that time, or that had been identified, in order of increasing atomic masses. And that was from left to right. He also left open spots where presumably yet undiscovered elements would fill in the periodic table. Also, because of this particular arrangement, elements with similar properties were put in the same row. Then, a bit later, in 1913, Moseley arranged the elements according to increasing atomic number, so the number of protons in the nucleus. And with this arrangement, elements with similar properties were ended up in the same column or family. So that is the arrangement of the periodic table today. And we have just learned to write electron configurations. And this depiction of the periodic table then shows us where the S block, the P block, the D block, and the F blocks are in this periodic table. And we already know the main group elements, group 1A to 8A, their location, transition metals, and then the inner transition metals at the bottom. And the periodic table then is a good way to help you write electron configurations, because you can just begin at hydrogen and trace through each row down to the next column and across again from left to right. So you don't have to memorize any of that. You just write the configurations based on that periodic table. Valence electrons, as we know, are the electrons that occupy the highest principal energy level in an atom. So they are in the outermost shell. The valence electrons are electrons that participate in chemical bonding or are lost or gained, or lost if you're a metal forming an ion, gained by nonmetals if you're forming an anion. But because elements within the same family or group have the same number of valence electrons, we can write a general electron configuration. And you are responsible for being able to write these configurations. So group A, all elements within group 1A have one valence electron. So N specifies the principal energy level, S the subshell, and we have one electron. So that is the general electron configuration for the valence electrons for the elements in group 1A. If we go to group 2A, we have added another proton and another electron, so the general valence electron configuration for group 2A metals is NS2, and this progresses all the way across those main group elements until we get to the noble gases. So we're just adding one proton and one electron as we move from left to right through that period or row. So for 3A, NS2, NP1, 4A, NS2, NP2, 5A, NS2, NP3, 6A, NS2, NP4, and 7A, NS2, NP5. Whoops, finally, and I guess, sorry it wasn't on there, the halogens would be NS2, NP6, having a full outer shell. So periodic groups. Elements in the same column have similar chemical and physical properties, and this is because they have the same number of valence electrons. Okay? So it's those valence electrons that participate in, as we mentioned before, bonding or ion formation. Okay? All right, so you are responsible for some of the names of the groups that are found on the periodic table, or the families. You don't need to know all of these. You do need to know the noble gases, which is, of course, 8A. So noble gases, halogens here, alkali metals or alkaline metals. These are the alkaline earth metals. So alkaline metals, alkaline earth metals. They don't show earth in the name of that. You know where the transition metals are, and of course the rare earth metals are down here. But these are the four groups that you will be tested on here. You know where the metalloids are located. It's across that along that zigzag line on the right-hand side of that periodic table. Let's see. All right. So before we actually start talking about the periodic trends, we're going to talk about something called effective nuclear charge first. And essentially what this is the given a particular electron in an element, the pull that particular electron feels from the positively charged nucleus. And it is affected by something called shielding, or the shielding effect. Okay? So as we move from left to right across the periodic table, we are adding protons, and when we're talking about neutral atoms, we're also, of course, adding electrons. And so as we move from left to right across a group, or a family, or row or period, we are increasing the positive charge in the nucleus. However, if there are shielding electrons present, and we're actually going to calculate some effective nuclear charges for some elements, so you can actually see this trend. Electrons occupying energy levels lower than the one your element of interest is in actually shield those outer electrons from that nuclear charge. Okay? So they protect them from feeling the full positive effect of that nucleus. So we're going to, you might also see this represented by the Z with a subscript EFF. And essentially, the nuclear charge effective nuclear charge is calculated by taking the atomic number, zeta, and subtracting it from it the number of shielding electrons in that atom. Okay? So if we look at hydrogen, excuse me, hydrogen's atomic number is 1. Highest N value is 1. There aren't any principal energy levels below it, so there are absolutely 0 shielding electrons in hydrogen. So the charge that electron in hydrogen feels from the nucleus is a +1. Now we're going to go over to helium. It's also in n = 1, but it has an atomic number of 2, still no shielding electrons, so the charge felt by the electrons in the helium atom is a +2. Now we're going up, or increasing, the principal energy level when we go to lithium. We are in n = 2, right? So atomic number for lithium is a 3, and there are 2 electrons shielding it. Those 2 electrons reside in the 1s orbital. Okay, so -2, lithium only feels a +1 from that nucleus that has 3 protons in it. So it's being shielded by the 2 electrons in the 1s orbital or subshell. So we're going to continue along across the period or row that lithium is in to boron, and we'll calculate effective nuclear charge all the way over to fluorine. So effective nuclear charge for boron then is going to be its atomic number 5 minus the 2 shielding electrons and the 1s, so it feels a +3 pull from the nucleus. Keep in mind, there are 5 protons there. It doesn't feel a +5, it feels a +3. Effective nuclear charge for carbon is 6 minus 2. So now we have a +4. So we're moving from left to right across the periodic table, and we see that effective nuclear charge increases. Okay. So zeta for nitrogen is 7 minus 2, so it's increased to a +5, but it's not feeling a +7. Zeta for oxygen, effective nuclear charge for oxygen is 8 minus 2, so it feels a +6. And then finally, for fluorine, we have 9 minus 2, or an effective nuclear charge of +7. Okay? So, this phenomenon, or this shielding effect and effective nuclear charge contribute to some of the periodic trends that we are going to talk about. So why does zeta increase, or effective nuclear charge increase, as we're moving across a period? Just to summarize what we've just discussed, the nuclear charge increases from left to right in a period because we are adding protons to the nucleus. We are also adding electrons. However, those electrons are not shielding electrons. The shielding electrons remain constant when you're moving from left to right across a period. They only increase when you go from one energy level to another. Okay, so those valence electrons also feel a larger positive charge from that nucleus because the shielding electrons remain constant. Okay, so those outer valence electrons are held tighter as we move from left to right. And that's, as I said, going to contribute to periodic trends that we're going to talk about. So I want you to keep that in mind to help us understand. So, periodic trends that we're going to look at: atomic radius and ionic radius, ionization energy, electronegativity, reactivity, and metallic character. So 5 periodic trends that you should be able to answer questions about. And I'll give you some examples in a handout or a worksheet that I have for you. You won't be turning it in, but it helps you take a look at what those trends are. Okay, so atomic radius. First, let me define what that is. And I'm not a great artist, but I'm going to draw 2 atoms here. Okay, nuclei are central. Okay. So, atomic radius is defined as 1/2 the distance between the nuclei on 2 adjacent atoms. Okay. And in large part, the atomic radius is determined by the strength of the attraction between the outer shell electrons and the nucleus. And the stronger the hold of the nucleus on the electrons, the smaller the atomic radius. So this trend can be explained by effective nuclear charge. So remember, we just saw that when moving left to right across a row or a period, adding electrons to the same subshell, these electrons cannot shield one another. So the nuclear charge is increasing, but shielding is not. So that nucleus has a stronger hold on the outer electrons, and the atomic radius decreases. Okay? So the trend, as you can see in this diagram or this figure, is that moving left to right across a period, atomic radius decreases. Okay? And if we are moving not a very good line, top to bottom in a family or a group, atomic radius increases. Okay? I've also posted a handout in this week's module that summarizes all of these periodic trends as well as how to write electron configurations. But think about this. As we go from n equals 2 to n equals 3, we're increasing the number of shielding electrons, because now all those electrons in n equal 2 can protect the n equal 3 electrons from that pull from the nucleus. Okay? So, as you go down a column, atomic radius increases. And if you go across a period left to right, atomic radius decreases, because that nuclear attraction is more positive or greater and stronger. Okay? All right.